Design World and the Motion Control Association. I'd like to thank everyone for joining us today. My name is Marshall Matheson. I'm with Design World and hosting today's webinar. And the webinar here is, hopefully at the right spot, it's Introduction to Servo Motion. And our presenter today is Gordon Ritchie, and he's a project manager, technical training for Cole Morgan. And before I hand it over to him, I just have a couple house cleaning items. As usual, this recording and a PDF of this presentation will be available online. And we'll go ahead and send out an email with those links after the presentation. And also, we're going to have questions for the end, so feel free to fire questions in, and then we'll go ahead and answer those at the end of the presentation. And also, I created a Twitter hashtag for those interested in the hashtag. It's a #, it's MCA Servo. So if you'd like to tweet about it, feel free, and we can pick up the feedback on that as well. So again, it's hashtag, it's a #, it's MCA Servo. So with that, I'd like to hand it over to Gordon, and take it away, please. Thanks.
Thank you very much, Marshall. Thank you, everyone, for joining. I'd like to thank Marshall and Design World for hosting this, as well as all the members of Motion Control Association. And as you mentioned, this is going to be an introduction to servos. And we look forward to your questions at the end. Now I'm going to see if I can progress through this. There we go. Now the main mission of Motion Control Association is to basically bring a higher awareness and understanding of motion control and how it can affect your business. It's a very good organization, and it has a lot of opportunities to help advance motion control throughout the world. And if you're not a member yet, should be. These are some of the companies that have already signed up for Motion Control Association. And as you can see, the list keeps growing. And for more information, you can go to Motion Control online. And let's get into the presentation. Again, we look forward to your questions at the end. And what I'm going to try to do is help you understand as much as you can about brushless servo motors and the technology and how they can be used in your different applications. So if we take a look at servos, or servoing, or exactly what it is, this is a definition that I've kind of put together over the years, and I've tweaked it a little bit here and there. But I'm pretty satisfied with this, that basically a servo is a device, electrical, mechanical, or electromechanical, that upon input of a stimulus, which is basically what you want it to do, your command, it will then employ feedback for velocity and or position control. And this creates a closed-loop system. So anytime we're talking about a servo, we're basically talking about a closed-loop system. And for it to be a closed-loop system, you have to have feedback in that system, somewhere in the loop. And probably one of the main advantages of a servo in motion control is that they are dynamic in how they perform. They're used in applications where precision is paramount to the application. And the way we do this is by closing the velocity and the position loops. Servo systems can provide very high accelerations and decelerations, and this will get you from point A to point B very quickly. And because we have complete control over the acceleration and deceleration, it'll give you very smooth control as well. All this plays in for a superior motion profile, which at the end of the day is going to give you better products and better performance, much higher throughput on your machine. What we really want to look at when we're looking for a servo going into a system is we're looking for something that is really motion dependent, where the actual motion of the product or the machinery that will be creating the product really requires the high performance that only a servo can give. The high acceleration, high deceleration, the very precise velocity control, very precise positioning. And what we find is that there are certain fields or certain application types that we really want to get into, because this is where the benefits of a servo really come into play. such as packaging and converting. Basically high-speed packaging, where you're taking millions of parts and placing them into the packages very quickly and very precisely, or converting, where you're taking a paper product and converting it into a magazine or a newspaper, high-precision documents such as security bonds or stocks. Then also electronic assembly. This is extremely important in the field of surface mount technology, where the components are getting smaller and their positioning on the circuit board requires much more precision in the control, as well as manufacturing of semiconductor items. When we start talking about semiconductors, now we're getting down into very, very small positioning tolerances and very high requirements for the precision in the equipment that is going to be manufacturing the components. Mistake in the semiconductor industry can basically trash a $300,000 wafer, and not only the money that's involved, but also the time in producing that component. Then we also have textile, which has a requirement for a very high throughput to keep costs down, because it's a very competitive market when you're working with textiles. And textiles can also include beyond just fabric for clothing, but also carpeting, which is also another high volume item. Then we have medical devices. I don't know about you, but I really like the idea of having my medical devices being very precise. Also, in the medical field, how they run, how quiet they are, is also very important. And the more precision you have in your system, the better that equipment is going to run and the quieter it will run. Then we have aerospace and defense, which is a very demanding field in itself, which also includes things beyond the aircraft or space shuttles, but also radio telescopes, where you're trying to hit a point that's millions of light years away. And then automated guided vehicles. This is a very exciting field. It's one that is growing in leaps and bounds. This is also used in manufacturing, where you may have forklifts that are automatic and will, at the end of the day, be able to take the product, store it in the right location, or pull that product and take it to the shipping docks. All of these are using servo technology. If we take a comparison of two different actuators, one that is servo-driven and one that is hydraulically driven, we can see that we've got a lot of benefits for both of them. The servo is a very easy item to replace, and I mean, as far as replacing the hydraulics, because most of the form factors for the actuators are very similar to the actuators you would have in a hydraulic system. Hydraulics would also include pneumatics as well as the fluid type. Servo actuators can have strokes up to 1.5 meters. There are no hydraulic or pneumatic lines that have to be routed. You don't get the fluid leaks. And with the pneumatics, you also have the sound of the valves as they kick on and off. Some of those are very noisy with very high decibels. One thing about a servo actuator is it can position the actuator very precisely in a midpoint. It doesn't require doing a full stroke for the application. And also in hydraulic systems, you have high pressures in the lines, and if a pinhole occurs, this can shoot out a jet of fluid that is paramount to a basically an abrasive jet cutting system. So it can be very dangerous. But some of the advantages that you do have in hydraulic actuators is they can produce high forces. They are rugged designs, and they're also very established in industry. And industry recognition is very important. But as we found over the years, as we convert people over to servo actuators, they find the reliability, the ease of connecting and also replacing actuators that may have failed is much quicker than when you go to a hydraulic system. And then the mess of the hydraulic fluids, which inevitably will leak out. So if we take a look at a servo motor and sort of dig into the anatomy of what we're talking about, we're talking about a three-phase motor, and you can see from the cutaway at the side, we've got a rotor on the inside which has the magnets. Mainly what we use are rare earth magnets, the granddaddy of which is the neodymium iron boron, which gives us very high torque capabilities. Servo motors are designed with torque in mind, and basically what we would do is we are controlling the torque of the motor, and that in turn gives us our velocity control and our position control. We have the velocity loop internal to the control system, as well as a position loop. Servo motors are inherently rated for continuous duty, and they have very high torques in the intermittent duty range. Servo motors have a tendency to be placed in very rugged housings and have robust designs. Internally, if we were to look at the servo system, we've got three-phase winding. The one on the top is a Y winding, and the one on the bottom is delta winding. And the design of the system helps us to close the different loops. We are controlling the three-phase of the Y-wound motor and also the delta wound. And we have the high power magnets internally, which gives us the high torque of the system. In addition to the electromechanics and the magnetics of the system, we have various feedbacks that are offered. The feedbacks allow us to adapt to the different applications that we'd have in the field. As far as the motor phasing goes, we're controlling all three phases, but at any given time, on a Y-wound motor, we're going to have current through two of the phases. And what we look at when we're setting up the servo system is we're looking at the phase relationship between phase A, B, C, or European standard UVW. And for clockwise rotation, you'll basically have the plots that you see in the chart to the right, where the top one is phase A or U, the middle one is phase B or V, and then the bottom one is phase C or W. And this is the phase relationship that we would see if we were to attach an oscilloscope. I've also included on this slide the phase relation between the Hall effects and the motor phases. You see that Hall effect 1 is aligned with phase A, which is also U, and then Hall 2 is aligned to our second phase, and then Hall 3, our third phase. Hall effects are needed when you're connecting to a feedback device that may be incremental. It does not have any absolute positioning to it. So when we begin our initial startup, we need to know where the magnets are in the rotor. So we add in the Hall effect devices, and this allows us to know the position of our rotor as we begin. The other thing about servo motors is that they come in a wide variety of housing types. We have our standard motor housing. If you look at the photographs, the top left photograph, which is a standard housing. It is sometimes called a sausage motor because they're long and standard looking. Just below it you see a direct drive motor. This is usually designed to have the load directly coupled to the motor. And below that you see a frameless parts set. And the frameless parts set is designed to go into a machine. Basically we remove the housing, the extra bearing, and the feedback device, and then you build it into your machine using the bearing of the machine as the motor bearing, and then you'll add your feedback device as you need for the system. Also to the top right, you see linear motors. They're also sold as part set and can be built into the machine. And then the cartridge motor below, which is like a regular motor except it has no bearing inside. It's designed to be attached to a machine using the machine's bearing. And then the photo to the bottom and left, that's an explosion-proof housing. It's designed to work in hazardous environments where there may be explosive gases. Explosion-proof doesn't mean that if gases get inside, it won't ignite, but it means that if that gas inside the motor does ignite, the housing is designed in such a way that it will contain that blast. So you can see that there are large varieties available, and these are all standard items that you're seeing. It doesn't include options where customer may want to design their own housing for a particular application. Customization is very important in the servo world. When we talk about motors, servo motors, stepper motors, brush type motors, we usually talk about them in two different ways. We talk about the frame and the stack length. The frame is what you see when you look head on with the motor. It's basically the square or round face of the motor. And that determines basically the air gap inside, or how large the rotor is going to be. And when we look at the frame, we're looking at the flange mount, which is where the bolt circle is located. We're also looking at the pilot diameter. That's the round circular area, which actually does most of the work in holding the motor in position. The bolts basically hold the motor up to the machine, but the pilot is what takes all the forces as the motor accelerates and decelerates. And then, of course, we have the shaft, and this would include the shaft diameter, the shaft length, and whether it has a keyway or some modification to the shaft. Then we have the stack of the motor. When we talk about the stack of a servo motor, we're looking at it from the side view. And the term stack actually comes from the laminations, which are internal to the motor. It's what the coils are wound around, and the teeth of the laminations become basically the electromagnet inside the motor. Well, these laminations are thin layers of ferrous material, which when the coil is energized becomes an electromagnet. And it takes a certain number of those to create a stack. For instance, it may take 12 thin laminations to create one stack. Well, if you were to say you have a two-stack motor, it would take basically 24 of those laminations, or twice as many as a single stack. So when we talk about frame and stack length, we're basically talking about the outside dimensions of the motor. And as those dimensions change, the amount of torque and velocity we can get out of the motor will also change. And then we've got feedback. And you can't talk about a servo without talking about feedback. Hall effect is the simplest feedback device, and it is added to a motor when you have an incremental device such as the incremental encoder. Incremental encoder is an optical device and been used for many, many years. We also have resolvers, which are an analog device. Resolvers are very robust in their design, and we use them today in applications that are very demanding, where there's a lot of vibration or G-forces applied to the system. And then we have the sine encoder, which is one of my favorite because we can get very high resolution out of the feedback device. In servo systems, we have to electronically turn on the windings, unlike a brush motor that is self-commutating. Brush motor that connects to a DC battery, you connect the battery and it begins to rotate. And as it rotates, it switches over from commutator bar to commutator bar, energizing the next set of windings as it rotates. And that's what we call mechanically commutated. But in a servo system, we don't have that luxury of the mechanical commutation. So what we do is we electronically commutate it. This is where the feedback device comes in, because to turn the windings on and off in the proper fashion, we have to know where the rotor position is at any given point in time. Servo systems will close the current loop, the velocity loop, and also the position loop. And in some cases, the position loop is actually closed by an external controller. These external controllers have a tendency to be higher level controllers with linear and circular interpolation. And they will take a servo system and turn it into a high-performing, very demanding dynamic system. And as you can see at the bottom, the main things that make up a servo system are the motor and the drive. The drive doing all the electronic commutation and the motor doing all the work. Inside the drive, you're going to find a current loop. And this current loop is based on the motor's inductance and the PWM signal that we're going to be putting into the motor. And what we'll do at the factory is we'll optimize this current loop for you. That way, as the system is tuned, you'll be able to increase the amount of performance that you get out of the system. We don't suggest that people adjust the current loop in the field, because if you get the current loop out of whack, you're basically affecting the velocity loop and the position loop after that. The velocity loop is probably the most common level that servos are controlled at. And even if you're taking a drive and controlling it in velocity loop, you may have an external controller that's actually doing the position loop. So it'll be sending velocity commands down to the drive. Or you may just have a standalone system that is running in velocity mode. Basically, in the velocity loop, we give this control over to our customers, because you have to tune the velocity loop based on the inertia and frictions and compliance that might be in the system. Compliance is something that is not very good in a system. It's the twisting, the backlash, it's the rubber band effect of devices that you may be connected to. And basically, when you have a high compliance system, you have to detune it or take away some of that performance. The reason we do this is because when you have a very demanding system, you want to get the gains up as high as possible. But if you have a compliant system, you get a momentary disconnect between the motor and the load. Even though physically they're still connected, in the servo world it looks like they have disconnected, and those gains cause the system to go unstable. So to maintain that, we have to detune the system. So it's very important to make sure we understand what we're connecting to and how rigid and how dynamic the mechanics of the system are. And what we'll do is we send a command in to the velocity command. The velocity loop will then look at the feedback and see where we are. And the difference between the commanded and the actual feedback is going to produce a velocity error. This error then drives the current loop. It sends the current command down. We look at what we're producing as far as current, and between the actual current and the commanded, we get the current error. And then this continues as we try to maintain our velocity control. Next step up from that is the position loop. It starts becoming very complex when you're looking at position, because you're not just looking at how fast it's running, but you're looking at where it is in space and time. You're looking at the position, the time, the velocity, acceleration, everything at all at one time. And this becomes very complex very quickly, especially if you're doing something like an S-curve acceleration, where you're actually smoothing out the beginning and the end of the acceleration and doing a constant velocity in between. The position loop works very similar to the velocity loop, where you have your command, you look at your position feedback, and then you produce an error. This then drives the velocity command, which looks at its feedback, produces an error, which drives the current, looks at its feedback, and produces the error, and so on. So you can see from this diagram, the current loop basically is the basis for the velocity loop. The velocity loop and the current loop are the basis for the position loop. And if you get the tuning for any of those loops out of whack, then we end up with a lower performing system. So when we actually tune the system, we begin from the current loop, work our way to the velocity loop, and then the position loop. Every system is put together with a motor and drive, and what we'll do is we'll plot that performance in what we call a speed-torque curve or a torque-speed curve. You notice the two curves look different, but if you were to look at the data, they're actually saying the same thing, except one has speed on the left-hand side and torque across the bottom, whereas the other one has torque on the left-hand side and speed across the bottom. Within the curves, you have two different areas. The blue area is the continuous, and this area you can stay in all day, all week, all year. The red area, that's what we call the intermittent or peak area. You're allowed to jump into that area and stay there for a little bit, but you must get out. This, the peak area is basically what we use when we begin to accelerate a load and decelerate a load. If you've ever tried to help your buddy push this car that just ran out of gas, you know that when you first start pushing it, it requires a lot more to get it going than once you get it going. Same thing in the servo world. So we have the peak area, which we can jump into, jump right back out, and then we can stay all day in the continuous if we want. When we size a servo system, we're looking at this peak and continuous region, and we're looking for 2 points. We're looking at, let me see if I can use some of the tools here. We're looking at this continuous region, and we're also using this region, which is the peak region. These two areas are the performance required based on the load, acceleration, and velocities that you want to run. If we aren't able to hit these two regions, for instance, if this peak region were to be out here somewhere, well, then we're not going to be able to actually make that move or perform that particular application, because it's outside the possibility of that servo system. Okay. And there's our continuous region and the peak region. Most drives today, because we have so much data coming back from our motor, because we're closing the loop and we know what the system is doing at any given point, have what's called a scope tool. And this allows us to catch those data points for selected parameters. And you notice in the diagram at the bottom, we're plotting the current, the velocity feedback, and also the velocity commanded. And this was for a particular move that was made on the system. And you can see that the red area, which is our current, we have the peak in the acceleration area right here. And we also have another peak right here that's in the deceleration area, because it requires as much to stop the load once we get it going as it does to get it going. Of course, friction and losses in the system sometimes help us to decelerate. This data can be very useful when we're setting up a system and trying to get the peak performance out of that particular system. This tool can be used also to tell us if we've got a problem in the systems. Sometimes we have mechanical issues, such as a loose coupling, and in the profile we'll see an anomaly that kind of looks like a little spike in the acceleration Then we see it again in the deceleration. As the loose coupling tightens up during the acceleration, we get that spike, and then as we start to decelerate, it'll open up again, and then we'll hit it again, and we'll get another spike. The scope tool is one of the more important tools that we have in the system, and it can clear up a lot of issues that you may have. Also, if a customer is concerned about whether they're actually getting the performance that they've requested, or if this machine just doesn't look like it's running as fast as it should, we can take a scope plot and we can show them exactly what it's doing. And in some cases, it may not be operating properly. Scope plot will tell us that, and we can adjust our system, adjust our gains, and whatever else we need to make sure we get the correct performance out of the system. And this is the last slide I have. This is another tool that we have available to us. This is called the Bode plot tool. Again, we've got the data that is coming back from our feedback devices. We know the position throughout time. Well, we can take a part of our system and we can excite it. We can excite the mechanics through the servo. And we can do this at different frequencies. If you look across the bottom of the plot, you can see we have a logarithmic scale here. Oops. And those are the different frequencies that we're actually putting into the servo system. As we change the frequency over time, we're going to hit different points in the mechanics. And what's going to show up are things such as loose couplings, compliance in the mechanics, such as if you have, in this particular case, we had a very long, thin screw that was connected to the motor through a low-end, basically a low-end coupling with a lot of compliance, a lot of play in it. Because we had so much of this going on in the system, we were able to get feedback on this through the Bode tool, and it was showing us where the different points were occurring. You can see we have a resonant point here and the anti-resonant point, and we can also look at the frequency here. If we were to go follow our system over, if we were to go down 3 dB, which would be right about here, we can actually figure out the bandwidth of this particular system. One of the standards that we're using today is that we'll take a Bode plot of a system before we even begin tuning the system. The reason we do this is to get a benchmark for the improvements that we might be making in the system through our tuning. Some of the things that we get out of the Bode tool is we can help the machine designers with their actual machines. We can show them how stiffening a coupling or stiffening the mechanics can actually improve their performance over the Bode tool. And all this will play in together to give the customer better performance. More performance on the machine side means that you're making better parts, or you're having higher throughput, or you're just having a higher quality machine. So as we look at this, what we're seeing is at this point right here where we get our resonance and anti-resonance, that's actually where the mechanics of the system are decoupling from the motor. And the further out we can get in this frequency, in many cases, the better it will be. But it's really based on the natural resonance of the system. You can tighten up a system at one point and actually see this resonance move out to another point. What we don't want is we don't want these resonances to happen down here in the lower frequency range. Those can give us a lot of problems, because if we look at the current velocity and position loop, the position loop is going to be somewhere around 200 hertz or less as far as the area that we're working in. And that is your introduction to servo motion. At this time, I'd like to pass it over to Marshall so we can open it up for any questions that we may have out there.
Yeah, thanks, Gordon. And so again, if anybody's got any questions, feel free just to, on your console on the right, you can go ahead and ask questions directly. Just have a couple here, though, I'd like to, we'll start out with, and not necessarily any order for your presentation, but there was one question on what's the advantage of a frameless motor?
Well, one of the big advantages is that it saves you space and it is directly coupled into the machine. By saving space, you're going to also save weight in the system. Also, a frameless motor doesn't have the bearing inside, so you're eliminating an additional bearing in the system. If you have this connected at the end of, say, a very large roll where you have 2 bearings on the roll already, if you have that 3rd bearing in the motor, then you've got a 3-bearing lineup, which becomes more difficult. By eliminating that, you remove that 3-bearing alignment, you're directly coupling it to the machine and you're saving space. So it really depends on the application. Sometimes it's not advantageous to go to a frameless motor.
Gotcha. All right, just looking through here. So there's another question here on how does system overall inertia affect the system performance? I guess this is in regard to maybe a velocity loop application.
Yes. In the current loop, we don't really worry about the inertia of the system because what we're trying to do is get as much current into the system as possible. But when we get into the velocity loop and the position loop, now we're accelerating the mass that may be connected to the motor. The greater the inertia out there, and the greater the current's going to be during this acceleration and deceleration. Also, the higher the inertia on the system, the higher the gains need to be to get motion going. If you have a very high inertial load, your gains are going to be very high, but if you have compliance in between there, such as a long shaft or a long belt drive system, now you got that momentary disconnect with ultra-high gains for the inertia. And this is where you can get into real problems with resonance in the systems and tuning issues. So the higher your gains, the higher the inertias in the system, the higher the gains will have to be, and it becomes more important to look at your mechanics because you're going to have to make sure you've got a very stiff system out there. Of course, if we're talking about direct drive system where you're taking the load and bolting it directly to the motor, inertia becomes a totally different issue because we're not as concerned about the inertia in the system at that point. The inertia of the system is basically the inertia of the motor.
All right, and there's a question that came in as far as related to the blade plots in the system. It was basically repeat, especially why you don't want resonance in lower frequency ranges.
Because the lower frequency ranges is basically where you're trying to control your position loop. If we look at the gains of the system, the current loop has the highest gain possible. And in one of our newest drives, that bandwidth in the system is going to be as high as 4,000 hertz. Then we step down by a factor of about 100 in most systems. So you're going to go from 4,000 hertz in the current loop bandwidth, and you're going to go down to 400 in the velocity loop, and then you're going to be down about 4 hertz in the position loop. So when you get down in that lower area, you're those resonance in that area are going to be fighting directly with your command in that area. So as you try to accelerate and hit one of those resonance points, then you're trying to compensate for that in the position loop. It becomes very tricky at that point. About the only thing you can do is to, we can add electronic filters into the system, or we can change the resonant point by stiffening the mechanics.
All right, and then there's another question came in regards to hydraulic systems. In comparison, when you have check valves with hydraulic systems, what checks are there in servo systems when you get to things like power outages and other stop gaps in the servo system compared to hydraulics?
That's a very good question. You could actually take a a actuator and connect it with a motor with a fail-safe brake on it, so that when we lose power in the system, the fail-safe brake, which is designed for power on, brake off operation, so when we lose power, then the brake is engaged. This will allow you to, if you're lifting a load, say vertically, and you lose power, the brake will kick in and it'll hold position. It works very similar to a check valve in the hydraulic systems.
All right. I guess there's also, along with that, there's probably some technology in the networks as well when you're connected to networks for that redundancy and safety.
There can be, but most of the time, if we're talking about a power out system, we look at it from the point of view that we have lost all intelligence to the system. So it's looking at only the mechanical stuff that we can add into it. And if we still have logic power, that's another issue, because we can actually dynamically break the system, which is taking the windings and putting them in connection with the regen resistor. And this will allow the back EMF of the motor to actually hold motor position. It relies on motion, so what we'd get is a very slow descent of the actuator as compared to a out-of-control descent of the actuator.
Understood. And another question here is there a rule of thumb for the range of motion? So the example is if there was a limitation, say the turn's only 180 degrees, the question is what is the realistic range of motion in such a case? So if I'm understanding the question here, can the full 180 be achieved?
Of the servo motor?
Yeah, I'm trying to clarify a little bit here. It's I guess with the limited servo range, I guess it's like a rule of thumb for the range. I don't know if it has to do with the application or how you specify the motor.
Well, we don't have any limitation on the rotation. I mean, servo motors are designed that they can run 1,000 RPMs all day long or 6,000 RPMs all day long. But we do have a limitation when you start doing very short moves, such as a very short oscillation back and forth where you're only going plus minus a few degrees. That limitation is based more on the bearings inside and the lubrication, how it gets dispersed throughout the motion. And what we want to see there is, it depends on the number of bearings and everything, but we generally say that we'd like to see about 15 degrees of, plus minus 15 degrees of rotation, just so that the lubrication is dispersed properly. We have done applications where the motion was very small, and it was within that limit that we don't like to get into. And so the customer would make these short back and forth motions, and then every once in a while they'd do 180 degrees and then back, just to help redistribute the lubrication and the bearings. That short motion is just basically pushing the lubricant off the surfaces, and then you get a nice bare spot with no lubricant.
I see. Interesting. So another question here: how do you decide what feedback device to use and when? So encoder versus resolver, or different types of feedback.
Well, in my experience, I usually go with the highest resolution feedback device to start with. I'd rather have much more resolution than I need than to have not enough. But then you have factors that come into play, such as a signed encoder, which is a very high resolution feedback device, is also very sensitive to high vibrations. So at that point, you got to start looking at what is the environment that this is going into. Also, things like encoders are susceptible to temperatures, particularly around 50 degrees Celsius. And so if you're in a very hot environment, such as a glass factory, then you don't want to go with an encoder. You want to go with something that's a little more substantial, like a resolver or smart feedback device. These have less susceptibility to heat, and they're also very good on vibration and shock loads. So rule of thumb for a feedback device is go with the highest resolution first, and then look at the environment and make sure that that will work in the environment that you're going into. I always tell my students that that servo sizing is like a teeter-totter. It's a balancing act. You want to put all the good stuff on one side and then look at the bad stuff, such as the environment and shock loading on the other side.
All right, I have an interesting question here. If you coupled the motor to a load with a very high inertial flexible coupling, is part of the coupling inertia added to the motor inertia for the purposes of calculating inertia ratio?
If I understood the question correctly, you've got a flexible coupling that has a high inertia as well. If that's the case, it's probably like a two-piece coupling with a flex plate or some flexible device in between. So half that coupling is going to be connected directly to the motor, and that portion of the inertia will be basically seen as part of the motor's inertia. But then everything on the other side of that coupling, the flex plate and the other half of the coupling, and then the load that is connected to that coupling, is going to be the reflected inertia that the motor is going to see. So yeah, when you're sizing, you would take part of that. But what we find usually in the field is that the coupling inertia itself is a very, very small portion of the overall inertia of the system. And most of the time it could be disregarded in an application. A few applications where customers have made their own coupling, and they have made a rigid coupling out of steel, and it had a substantial amount of inertia. That's one of the rare cases, though, you will see.
Gotcha, gotcha. In terms of system compliance, is there a rule of thumb for length where a belt makes more sense than a ball screw?
Well, when we start sizing and we're looking at a screw versus a belt drive system, we normally think of a screw as having a higher amount of force in the system and the belt having high speed. So you're kind of looking at which one is going to do the performance that you need. If both the screw and the belt will do the same amount of performance, that's when we start looking at the compliance of the system. Now, the belts have improved over the years, and they have a lot less compliance than they used to. But I would then go back, even if you had a long screw and a long belt for the application. Well, let's say it's a ridiculous length of maybe 5 meters of travel. At that point, it's not really going to matter if you go with a screw or a belt. You're going to take a look at the reflected inertia back to the motor, and if I was going that length, I would want the inertia reflected back to the motor to be 1-to-1 with the motor. That's simply because if you get higher than that with those lengths, you're not going to be able to tune the system very well. It's going to be very poor performing. I wish I had a number I could just throw out there, that if you have this inertia, you could go this many feet or this many meters. But there are so many factors to take into account that there's no real set number for that.
Gotcha. Another question here. Are there any problems associated with small frame size and long stack lengths?
Actually, there could be problems associated with small frames, long stacks, or larger frames and long stacks. It has to do with the ratio of the frame to the length. When you get in, let's say, a proportion where the frame is maybe 1/5 of the rotor length, you start getting into an area where you can actually get resonance created inside the motor itself, because you have, if you think of this long shaft that the magnets are going to be bonded to inside the motor, as you're putting torque on it and it's rotating, it is going to have its own natural resonance. And when that relationship gets longer and longer and longer, then you're going to end up with more problems. So you could have a very small motor with a small frame but a very long stack length. It could have resonance problems. Just as you could have a larger frame size, but if you went with a ridiculously long stack length, you could have the same issues in there. It's just like connecting to a long shaft on the load side.
All right, and then there was a question for addressing the need for gear reducing heads, and when are they needed?
Ooh, gear heads. We add gear heads in Usually when we don't have enough torque out of the motor and we have a lot of headroom on speed, we size the system up, for instance, and we find that we're only doing 50 RPM on the motor, but we're going to get into a ridiculously large motor for the application if we go directly coupled to it. So then we start looking at, can we get more mechanical advantage out of the system? So if you have a 50 RPM application and you have a 3,000 RPM motor, then we got a lot of headroom there as far as the gear ratio we can apply to the system. And then it's going to give us that mechanical advantage. We also look at using the gear head when we have a very high inertia mismatch. That's because we get the advantage of the ratio of the gear head squared as far as reflecting the inertia. Let's say we had a 25-to-1 inertia ratio between the motor and the load. If we add a 5-to-1 gear head in there, now we've got the 5-to-1 squared, which means we're going to reduce our 25-to-1 inertia ratio down to a 1-to-1 inertia ratio, and we'll be able to get better performance. Again, we're back to that teeter-totter. We add more gear ratio in there. We got to watch our speed now. The gear ratio gives us more torque, but it's also going to mean that our motor speed is going to have to be higher to give us the same speed out at the application side.
All right, and I guess I have time for one more question here, and this one a little tricky here. It says on an S-curve system, is starting the load versus stopping the load have any real major difference that should be considered for the mechanical design? And I guess the add-on is the example would be adding some shock absorbers or whatnot to help the stop cycle.
When we do servo systems, we don't really look at any outside device stopping the motor. We like the servo to do all the stopping. But if you were going to be bringing the load into a stop using bumpers in the system, I can't say that I've really ever have done that. We usually add bumpers in as a safety in case the system, something happens in the system and it can crash. But as far as accelerating and decelerating, we look at those as basically being the same thing. We know we need a certain amount of torque to get the load started, and we know we need a certain amount of torque to get it stopped, and we size it accordingly to make sure that the servo can actually stop the system. One thing that we do take into account when we do an S-curve acceleration, if you're doing just basically a 1/3 trap, where 1/3 of your time is accelerating, 1/3 of your time is at constant velocity, and 1/3 time is decelerating. If you were then to add an S-curve to the front, the acceleration side, and an S-curve to the deceleration side, with the same amount of time to accelerate the load, you're actually going to have to accelerate quicker once you get past the S portion and begin your acceleration. So you're going to require much more current out of the system. I love S-curve accelerations because they take a lot of stress off the mechanics, but we just have to take into account that you are going to require more out of the system and then size it accordingly.
All right. Hey, well, Gordon, thanks very much. Appreciate your time here. It was very useful, educational, and I just wanted to thank everybody again for tuning in. And again, if you've registered and you're here, also we'll get an email out to you and point you in the direction to get the PowerPoint slides and also the video. So thanks again, everyone, and thanks again, Richie.
Thank you, Marshall.